ArcSan is now digital.ai. Join us at our booth in the virtual expo hall to learn how our app protection, white box cryptography, and threat analytics solutions can help you stay ahead of the evolving threat landscape.
Welcome, everyone, and thank you for joining us today to talk about static analysis. My name is Adrian Bravo, and I'm a security engineer at Workday, and I'm going to be joined today by Gonella, who's also a security engineer at Workday. Before we get into the topic today, I wanted to share first some of the assumptions we've made about the target audience of this talk. So we're assuming that this is going to be most useful for mid-sized companies. So you're not so small that you cannot afford to purchase some of these tools or to dedicate a couple of engineers for an extended period of time onto this project. But you're also not so large that you'd rather just go and hire a full team of PhDs to build a custom static analysis tool from scratch, right? We all agree that that's probably the ideal solution for everyone, but we're not everyone is able to afford that. So we hope that if you're in the middle sweet spot, this will be useful to you. You will notice too that we've constructed all this architecture around not disturbing developer workflows. So we don't want the developers to have to change their IDE or the repositories or their pipelines. We want them to be able to do what they do normally, but still get the benefits of static analysis. Before we begin with the architecture, I want to highlight too the fact that you're going to see the steps we took to get to our current design. We're going to show you maybe some failed avenues, some dead ends or roadblocks that we hope that you don't have to take if you see this presentation. And that will also inform you about how we thought about this and how we went about building what we've built. OK, so let's start. The first thing that you need to do is obviously selecting a core for your static analysis platform, right? So unfortunately, for most of us, this is going to be an exercise in bad option. The reason for that is that there is nothing out there that will just work, right? There's nothing that you can go out and download, install, and expect to get accurate, good results out of it. In addition to that, a lot of these tools are quite expensive. You can obviously go down the open source route, but you have to make sure that the open source tools you choose can cope with whatever languages and platforms your company uses. And also that you're OK with the quality of the results that those open source tools are gonna give you, right? For us, that's not the case. So we ended up considering 6 vendors for this evaluation. And our biggest constraint getting into this was the fact that we needed the vendor to support Scala, because Scala is the second most used language at Workday. So that ruled out a lot of the potential candidates for evaluation, right? I understand that that's probably not the case for most of you in the audience, so that you will have more options to choose at this stage, right? We unfortunately didn't. The last point I want to make here is that when you're doing this piece, be really thorough. It is quite expensive, especially in time, to swap a vendor out to put another one. Even though we've tried to design this architecture in a way that we decouple as much as possible from the actual piece of software we are using, and that we are continuing to evolve this architecture in the future to do so, it still have a lot of interactions with the vendor product. So there's going to be a lot of time and effort needed to just replace that. So at this stage, when you're evaluating, make sure that you write some automation against the APIs that you're interested in. Make sure that if you expand the product, that you write some custom rules for that product. Most of these products will allow you to write custom rules to extend the type of findings they can detect. Do that, write a couple ones, and make sure that you triage at least a few issues to see how that flow looks like, how complicated it is to go through the findings and figure out whether it's a false positive or a real finding, right? Just be quite thorough here. Do not make any assumptions. Just don't trust and also verify. Now, when comparing products, there are 2 key things that I want to share with you. I think for us, it was very useful, and we strongly encourage you to establish a predefined criteria. Before you go out and start looking at vendors and what can you buy or not buy or use or not use, just sit down and write down all of these criteria that you consider important and relevant for your tool, right? For us, most of it revolved around automation and about the quality of the results, false positive ratio, false negative ratio, things like that. And this is the sample, not all of them, just a screenshot of part of the page with some of the criteria that we had. And we had some weights assigned to those and some disqualifying criteria. So if one of those, for example, is not met, that tool cannot, we're not going to continue to evaluate that tool. And you can see the mention of Scala and Java that I made before is here, right? Then you can go through your tools and like you can score them against all of these criteria, and you can use that in the way to obtain a numerical value that you can use to compare these tools on a more objective front. The last thing when comparing these products that I want to recommend is to select an internal corpus of application samples. I know a lot of the vendors will come with prepackaged results saying, hey, we did great against this or that well-known sample application. Problem with that, with those sample applications like OWASP web code and the use shop and the non-vulnerable web application, is that the vendors tailor their applications, their scanners against those. So they're always going to perform really good, but that's not really how they're going to perform against real world applications, right? So use your own code base. We did prepare 46 vulnerable samples from different applications at Workday, things that we patched and knew were there. And we ran these vendors through those. And you can see on the screen 2 of those vendors comparisons, right? We knew we had 46 vulnerabilities, and we knew that 45 found 47% of those, whereas Checkmarks found 17% of those. We also measure the max scan time, an average scan time, performance, and other indicators. We had a false positive ratio on a vulnerability or on a scan by scan basis. We also took 6 applications from Workday that we didn't know whether they were vulnerable or not, and we ran the whole scan on them. And we use that to measure noise in a way to see how much noise is in this finding report and how hard it is to identify an issue within that noise. And then we could get some of those false positive ratios. And all those numbers plus the criteria below that before allow us to basically just compare these vendors, right? So now you have your tool, and ideally for us, we wanted to have a fully automated pipeline. We wanted the developer to just go write the code, pushes the code goes through the pipeline. We pick it up at some point, scan it back to the developer. No application security engineering involved, all fully automated. Now, that's kind of like the holy grail, and it's probably unattainable, but we can strive for something around the 80-20 mark, where we have about 20% false positive rate. And if we get there, developers are usually okay getting those results, whether like when one in 5 is going to be a false positive and the rest are going to be good value, right? Otherwise, you're going to end up like the developer, like the picture there, with 7,495 results, which is a vanilla scan of one of our applications with no settings or configurations whatsoever. And that's obviously going to annoy your developers and erode any trust they have in your program. The challenge, though, to get to that 80-20 is, as you can see in the picture, the high number of false positives. We went about that in a few different ways. We attacked this problem from different fronts. So first, we used filters and views. Filters, in the case of our particular product, they're a little bit different, but most products will allow you to do some form of this. Filters allow you to remove some category of vulnerabilities or findings before the translation of the scan happens. So you speed up the translation scan a little bit, and they are never in the report. And then views are a way to just kind of hide or filter some of the findings from your report. But you can always go there and expand your filter, your view, and see all those other things, right? So for views, we filter those views based on category, right? That's obviously a good thing you can do. Say, well, I only care about cross-site script, SQL injection, this, and that, and everything else goes away. So you can focus and narrow focus on that. You can always expand the amount of type of vulnerability you care as your program matures. And then 45, for example, has a lot of numerical indicators about the accuracy of a particular finding. So you will find the confidence, the impact, the accuracy, likelihood, etc. We use all of those. We set some thresholds for them. And if the finding is below the thresholds for these values, we will ignore that finding, right? So if we have a finding that has a likelihood of 1 out of 5 and an accuracy of like 2 out of 5, we may say, well, this finding is not probably worth looking into in an automated fashion. So we're just going to push it away and not report it. And the last one to use for filtering and views, but probably the most important one, is the analyzer. Now, this is not a talk about how static analysis works, but most of these tools will come with a different set of analyzers. they will come with something like a semantic or a structural analyzer, right? Which is basically like grep. You can think about it like grep or like a structural match in the structure of the code, and they will use that to report certain vulnerabilities. That is usually less accurate than the analyzer that we care about, which is the data flow analyzer. The data flow analyzer is the one in charge of tracking and tracing the user input from the entry points in your program all the way through your code execution until it gets to a function that is deemed either vulnerable or dangerous. And those are usually more accurate results. So we filter out anything else that is not the data flow analyzer for our purpose. Second, we've been disabling bad rules or rules that come with the product, but that we consider to be too noisy, or that we just consider them to be plain wrong, that is reporting something that is not accurate. So we can disable those and save us some trouble. But you can also create new rules that either reduce the number of false positives by informing the tool about maybe Workday custom functions that sanitize input, or by adding context to the scanning. Or you can add custom rules to enhance the amount of findings the tool can find, right? You can talk about specific libraries or functions in your own company that you may want to raise an issue about if user data gets into those, right? The last bit here is profiling each rule's effectiveness. We have started collecting the data here, and we will start profiling soon, but we haven't gotten enough data so that the results will be statistically significant. Nonetheless, the idea here is to get enough data, enough findings and triage results for a particular rule against all our different applications where we're running it against, and say, well, this rule works very well in Java against this type of frameworks, but not so well against this other type of frameworks or this other type of applications at Workday that may have convoluted code or weird structures. And based on that, we can also decide whether we report that to developers or we keep it to ourselves. So that is something definitely we're still trying to work on, getting more data so that when we make a decision about the accuracy, we have a statistically significant sample. Okay, we can now talk about the phase 1 MVP architecture for this project. Before I get you into how that looks like, I want to spend a second here on what happened before there. So the vendor, in our case, a few of the ones that we evaluated, they just provide you with some packaging, and most of the times it's just some zip or compressed package that contains either multiple or a single service for the product. But obviously that's not something we can go and deploy in an automated fashion, in a dynamic way, and DevOps style, right? So we built some automation that you put the latest package from this vendor on an S3 bucket, and then we pull it down, split it into RPMs for all the different components of their product, create AMIs for all of those, and then use Terraform to create an environment that we can recreate, destroy, and modify dynamically as we need it. With that out of the way, this is what a scanning pipeline at a very high level usually looks like. Again, this is not a talk about static analysis in depth, but most of the time, this is what you're going to conceptually think about. You have your source code. You're going to go through a translation phase where the original language, in this case Java, is going to be translated, or Python or whatever, is going to be translated into an intermediate representation that the scanner is going to use to analyze and find vulnerabilities in. For us, with the vendor we selected, we had a binary called source analyzer that performs both stages. You have to run it twice with different flags, but it's the same binary. You just run it once for translation, and then you pass the translation into the scanner one, and you get your results. We had to build, though, another service on top of the vendor one to help with the translation phase. Now, you're wondering, well, if you said that the vendor already does the translation, why do you need to create your own service around this? And the answer is, well, the vendor does the translation, yes, but it doesn't actually know how to build all your applications. And Workday's code, unfortunately, is quite complex and very diverse. We let the developers do whatever they want with their products. So we end up having, multiple Artifactory instances where the dependencies exist. We have GitHub, Bitbucket, GitLab, Gerrit. We have multiple instances of some of these. We have Gradle and Maven. We have SVT. There's obviously Node and Python. All these things, are built and compiled differently. So we needed this service, Fortnite, to abstract the complexities around all of that. So the way this works is, well, obviously we have a lot of code in Fortnite that tries to identify patterns and knows about our applications and our environments and selects the right places. But we also have created this file where we create an entry for each of the projects that we are tracking and scanning. And we provide some metadata for Fortnite to be able to know what to do with some of these. And as you can see here, well, we support things like exclude. So if you have some files or folders that are either test files or with third-party dependencies that your developers they decide to pull into the repo instead of reference externally, you can exclude those from your translation scan. We have support for different branches. Most of the teams that work may use master, but some teams will have feature branches. So we need to know what branches we're trying to track. So we put that there. We have support for the multiple artifactory instances through the property prefix entry there in the file. And multiple languages, obviously. We can have one language per repo, or a repo can have multiple languages. We just put it into a field here so that we know that we need to translate the code for all these particular languages. And that takes us to the meaty part of this file, which is the build tool and the build command. The build tool is basically what I was talking about before. You can use Gradle, you can use Ant, you can use pipenv, or whatever else, right, that we have at Workday. And then the build command will tell Fortnite what is the actual command that it needs to execute in order to translate that code. If you look at the last example on this slide, you can see that this build command is quite messy. It goes into a folder, it sources a shell script with environment variables, and then it invokes a bunch of Ant targets to translate this code. And that is as much as we'd allow it to get into one of these build command instructions. The other ones you can see, maybe the Gradle one is just clean assemble, which is pretty simple. If it gets any more complicated than that last one, then we use what we call the build tools script. And what we do there is we basically tell Fortnite, hey, this is beyond your abilities. So just run this script we're giving you. It's going to do the translation for you. And it's a escape hatch we have for when things get really, really complicated. The Fortnite will invoke the script with a series of environment variables that contain maybe credentials for our factory environments or certain other configuration flags that we need when we're trying to write the scripts. And we'll write the script and do whatever needs to be done. And if you're wondering what that looks like, well, we have some developers that maybe, I don't know, go to an S3 bucket to download certain artifacts before you can build the code. Or they require to build this particular repository, they require you to clone a different repository and put it in a particular location in your file system. Or maybe a file that has to have a specific content. The file doesn't come with the repository they have, but it needs to exist with a particular name, and it has to have whatever content they decided. So all of those things and more we can do in the script when things get absolutely complicated, more complicated than this model can handle. Okay, and with that said, this is what the phase one architecture looked like for us. We had the translation phase done by Fortnite on the left on its own EC2 instance. We had an EC2 instance in the middle running the SSC, which is part of the vendor solution. Is basically their web UI. It has the APIs and their portal, so you can go in and look at the findings and stats and do some triage there if you wanted to. We don't use that. It's for us. You'll see as we evolve, but for us, it's basically become some sort of database wrapper, like a storage or something. And then we have two scanners in this case, two workers on the right. Those are running the vendor's cloud worker software, which takes jobs from SSC and scans and produces the results. On top of that, we needed to create another service called Foursquare that you can see there, and I'll talk about momentarily. But before that, I want to highlight the fact that at this point, there is no scaling capabilities. We have two nodes, and those are static, and they cannot go anywhere else. They cannot scale in or scale out, scale down based on load, so they're always going to be running. The vendor doesn't provide any way for scaling. Yes, you can decide how many nodes you want, but it's going to be a static number all the time. Now, Foursquare is a service that we wrote in the spirit of trying to decouple from the vendor software and also to try and unify the workflow for us and the developers. So developers at Workday and security teams will track all bugs and issues identified in Jira. So what we do with Foursquare is we go to the API of the vendor's software, the SSC, and then we just list the issues that were reported in the latest scan. And we try to create JIRAs for all of those if they haven't been reported before. Foursquare has its own internal database that you can check against for state, and it will create all the new things. It also can track things when they change. So if an issue disappears from a scan result because it has been fixed maybe, or because the file has been removed, then Foursquare will go to Jira and close that Jira for us. And it also has all like the Jiras that it creates, right? They're grouped by sync, which is the vulnerable location in the code. So when two vulnerabilities are reported that happen on the same maybe line and function, then Foursquare will create those Jiras grouped under like one parent Jira and some subtasks. So that allows us to triage more efficiently and also to pass it to developers, and they can work on a fix for all of those issues that are related. Lastly, the Jiras contain all the information the developer will need to work on it and make sense of the issue and produce a fix. It will have all the call stack traces. It will have a snippet of code where the issue resides. It will have some metadata about what type of issue it is, how to fix it. And some of the numerical values that we talk about for confidence will also be there. Now, if you remember, we said, well, there's no scaling capabilities in this, right? So that is a problem, but it becomes a bigger problem by the fact that both the translating box and the scanners, they require huge boxes in AWS. They are especially very memory intensive. So we're using these 12x larges, which I believe ship with 128 gigabytes of RAM. And they are quite expensive to keep around. So when we have not enough things to scan, we have a bunch of boxes that are idling and spending a lot of money. And when we have more than 2 or 3, or whatever the number is at the same time, we create some congestion. And then that's not ideal on either side. So we needed to figure out a better way to make this environment more dynamic. Now, you can say, well, can you not just go and scale this with AWS auto-scaling groups, since you're already in AWS? And that is right, and that's like probably the reasonable path to follow. We tried that. We tried it based on like CloudWatch metrics for CPU, for example. That was not very accurate. And then we tried with custom metrics we wrote a service for that my partner will talk about in a second. But it didn't matter however we went about this problem. The issue remained that we cannot control the worker third-party service, right? It is part of the vendor's product, and it will just pick jobs from the queue and work on those jobs and report the results, and we cannot touch how it does that. And it's completely unaware of any type of auto-scaling that is going around. So we run immediately into a lot of race conditions. For example, the autoscaler may have decided that this instance needs to die. It's like, we are going to scale this in, you're going to go away. But the software in it doesn't know about that. So it's going to go to the API and see there's still some work there, may pick it up, start working on it, and then 20 seconds later, the instance is terminated by the autoscaler. That job disappears and is never scanned, and we lost a lot of scans that way, right? So we needed to make changes to how we architected this, and we needed to think about how we're going to interact with the product in a way that solves this problem. And that's what my partner, Nick, is going to be telling you about in the phase 2 and the second part of this presentation.
Thanks, Adrian. So we're left with this kind of awful worst of both worlds, where the cloud worker has this race condition that's dropping scans, but we still do want to be able to auto-scale it, because we don't want to just have to have either boxes sitting around spending lots of money, or just have this very slow pipeline and lose our performance. And we looked at a lot of different ways of how we could actually go about this. And ultimately, what we came up with was the idea of adding this service called CloudFort. Now, CloudFort, you'll see here, is pretty much replacing what that cloud worker was doing. You'll see the big change between this and our last diagram was, instead of having those 2 worker boxes, we now have CloudFort in an auto-scaling group, and we've also added the service FortWatch, which I'll come back to in a moment. So we already know that we have the actual Fortify binary, which allows us to do the scanning. So what we're really left with is we need to get something that can interact with SSC and be able to pretend that it's a cloud worker and speak that same protocol. Now, When we set about this, we looked for the documentation, and unfortunately, the documentation between SSC and the cloud worker was not there. So we had to look into this undocumented API using MIDM proxy. Doing that, we were able to determine it was a relatively simple protocol. It was XML data-based, so no RPC and a relatively simple state machine. It was just saying that the SSC says hello, the cloud worker sends back an authentication packet, which was done with a pre-shared secret, and then they start waiting. They start waiting for jobs to show up. And what's super nice about this is we don't actually have just a single dispatch request, but rather we have a three-way handshake between the two, where the SSC will say a job is available, and the cloud worker can then say, yes, I'd like to claim this job. If the cloud worker sends that job claim, a claim acknowledgement is sent back, and only then does SSC register, yes, this job has successfully been dispatched. We are successfully sending this to scan. Once SSC does that, it then proceeds to send a massive binary blob, which we were able to take, write to a file, and that file was able to be imported into the Fortify binary for scanning. We would run the Fortify binary to scan that and effectively come out with a result file, which we could then send back to SSC using the same protocol. So we've done it. We now have a way to deal with this auto-scaling problem, because what we can do is we can utilize that job claim acknowledge claim framework to only claim a job once we have guaranteed that our instance can't die. So the next question becomes, how do you guarantee that the instance won't die? Well, we looked at a couple different things, a couple of the controls, and what we really determined is, as much as you try to fight it, there's always a little bit of a race condition when you check. And the only way to really ensure it is to actually try to enable instance protection. What we would do is we would receive this job available request, and then immediately would say, oh, all right, I have a job available. Then I will try to enable instance protection. I will immediately try to say, all right, I do not want this instance to be killed. Assuming that that's succeeded and that we were able to actually get that instance protection, only then would we send the job claim. Because sometimes instance protection would actually fail, which meant internally the instance was scheduled to die, but we didn't know it yet and couldn't actually see it through the API. So we send this job claim, and we kind of understand that, we're now slowing this thing down greatly, and someone else could claim that job before us, which is perfectly fine. We send the job claim, and if we don't receive an acknowledgement, if we're told someone else claimed it, we can go back to just being a regular instance. Otherwise, now we've received the acknowledged claim and we're protected. So now we can safely say this scan will complete. And we lose the problem of that race condition, which again, deals with the cloud worker problem. So awesome, we got it. We now have a working worker that can now scan things and scale up. The sort of question that comes next is, all right, we're doing the scaling. How are we going to do that? And again, for that, we had to make a few decisions, talk about a few different points. We tossed around the idea of CPU utilization, potentially box metrics, things like that. And what it ultimately came back to is, when we're doing this auto-scaling group, we need to make two decisions. We need to decide, when do we need more boxes and when do we need less boxes? And at the end of the day, when we need more boxes is when we have more scans that can't get serviced. So SSC has this queue of all of the translations that it's been given that it wants to send out for scanning. And if there are more translations in the queue than boxes, we need more boxes. If there are less translations in the queue than boxes, we can start ratcheting that back. And we wanted to use that metric as the way to determine what should we be scaling with. Unfortunately, it isn't that easy. AWS scaling metrics are traditionally to be used with things that AWS already knows about. So again, these are things like CPU utilization or box counts. But AWS doesn't really have a way to dig into SSC. It doesn't know how to talk to it, and it shouldn't have to. So what we ended up doing is creating FortWatch. This was that service that I mentioned earlier, and its whole job is just to keep track of a ratio. FortWatch knows how to talk to SSC as well as AWS, and it can get that ratio we're looking for of jobs in the queue to number of boxes. It will compute that ratio for us, and it will perpetually send that up to AWS as a custom metric. Custom metrics are a bit of a backdoor that's enabled in AWS that allows you to, if you really can't do it with their system, you can just report to this particular thing. And what we can do there then is have this metric. And now all we need to do with the ASG is say, okay, if we get above some threshold, 120, then we know the ratio of queue jobs we have to actual boxes is too high, give me more boxes. Or the ratio of queue boxes to jobs we have is too low, start scaling those back. And with that in tow, with that ability to scale solved, we have a working SAST platform. This is now scanning in a massively parallel way. We're able to get almost 1 box per scan, sometimes a couple in serial, but for the most part, we're scanning very well, and we don't have this problem of having to keep those boxes up all the time. And this was actually how we kept our system for a relatively long period to the lifetime of this entire system. But eventually, we sort of came across a problem that comes from the design of our repos. So our repos are, in addition to being polyglot, they're poly-size. We have both multiple monolithic repos as well as many microservice repos. And so what will happen is, eventually, at some point, the monolithic repos will start to build up and slow down this translation queue. And the reason for that is, while Fortify does offer some rudimentary ability to do And the reason for that is, while Fortify does offer some rudimentary ability to do incremental scanning, it wasn't actually usable for our situation. And so if we want to scan a repo, it's all or nothing. We have to scan everything or nothing. Now, because of these monolithic repos, they have more code, which means they change more frequently. And again, remember, we are scanning on a per commit basis in the ideal world. So what will happen is these monolithic repos will just build up scans over and over, and they take even longer to scan, starving our microservices. And so we have the problem of just, we can't actually get our microservices through because we're scanning multiple copies of the same couple monolithic repos. And this wasn't really a viable solution for us. We needed some way to be able to say, all right, I can't do this. So instead, what we're going to do now is we are going to take Fortnite and we are going to make it parallelizable just like we did with Cloud4. Now, we're going to venture into a very well-trodden area, and that is the area of, I wrote a program that was designed to be single-threaded, single-processed, single machine, and now I want to distribute it. This is a problem that many different pieces of software have faced over the years, and we ran into some of the same problems that they did. And that problem is one that is very well trodden, and that is, I wrote something for a single-threaded application, and now I want to make it distributed. So we're going to face a lot of the issues that others have, things like state. We wrote Fortnite to have state on the box and rely on that state, to be able to rely on it between and across runs. This also means that if we're going to be bringing these services up and down, we can't amateurize over caching. And what I mean by that is to say is, often when we have these auto-scaling boxes, Fortnite will come up, run 1 or 2 scans, and then die. So any caches that we populate with the first scan are going to be useful maybe one more time, but not much further than that. So it needs to be fast the first time. And of course, there are going to be race conditions. When you write something single-threaded, it is very hard to, unless you are really thinking, I'm going to distribute this later, not write it without any race conditions. Now, The flip side of the coin of dealing with a problem that everyone has already dealt with is there are people who have dealt with it before. We can go out and search out those solutions. And we actually ended up coming up with a pattern that was very, very similar to the fan in, fan out pattern, which is this idea that I show on the graph here. What's basically happened is we're going to take Fortnite and we're going to push all of the stateful and critical sections to the edges and try to offload them into either an orchestration part or a collection part. That way, our workers can be as stateless as possible while still doing the job, and we can only have one orchestrator or one collection that doesn't have to do any of the heavy lifting work that we're going to distribute across our workers. To accomplish this, we employed SSC as our collection. So SSC was the thing that actually ended up holding all of these artifacts, and it's very well equipped to do that. It is completely ready to have multiple translations submitted to it at the same time. However, on the other side, we actually were able to use AWS's SQS. Now, SQS is the simple queue service, and honestly, this is something I really just have to take my hat off to AWS for. It's a simple tool, it's a simple prospect. It's the idea of, I want a queue, I don't want to manage it. I want to be able to put stuff in and take stuff out. I want it to be consistent, reliable, and be able to handle massive requests. And AWS just gives that to you. And so I really am quite a fan of these style of services in AWS, where they just are a small thing that works quite well. So way to stay Unixy, AWS. Thank you. But a queue is not really going to be enough, because a queue can't actually do operations and logic. So if we want to get rid of those critical sections, we're going to need to go one step further. And we accomplish that with Fortifeed. So Fortifeed is our final service that we're going to add to this mix. And its job is just to do the initial setup stateful critical sections that Fortnite was originally doing. And what I mean by that is it's going to mostly decide what to scan. Fortnite originally dealt with that by looking at Git commits. So what Fortifeed will now do is look at that build file that Adrian showed you earlier. It will go and find all of the latest commits and compare those to, okay, well, what were the commits last time I ran? And by keeping track of those differences, it knows if I see a difference, I can send one of those on. And that's how it knows what to put in the SQS. This then in turn can be read from SQS. And what we actually end up doing is sending each of those individual objects that you saw in Adrian's slide. It sends each of those into the queue to be retaken out by Fortnite. Fortnite already knows how to read those object files because of the code we wrote for it originally. And it can just take that one project, translate it, and send it off to SSC. It's none the wiser, and we don't now we have an application that is relatively distributed and pretty stateless between runs. This was an awesome breakthrough to have, but it actually also led to a problem that we didn't really realize we would have until we started getting into debugging, and that was the problem of logs. So when you're running a single application on a single thread, if something breaks, at the end of the day, if you really need to, you can SSH into the box and grab the physical logs and go look at them. It's not the prettiest way, but it works. That's not true when you're dealing with an auto-scaling service. Many times we would have runs going at 2, 3 in the morning, and these boxes would spin up, try to run, hit some kind of error, and then clean themselves up. They're done. They're no longer scanning anything, so AWS would say, yep, this box is good to go. It's not protected, so it would get rid of it. And our logs would disappear. So we needed to get the logs off the actual file system and into something else. And the solution we ended up going with was another AWS product called CloudWatch. Now, CloudWatch is a log ingester, very similar to Splunk. In fact, it actually has a dashboard and some basic SPL-style queries that you can run on it, which was really nice to have for the logs. We could now look at things by service or by error type. But what was really useful was this log segmentation via streams. So you can configure these streams in any arbitrary configuration you want. We were able to configure them using Watchtower, which is a Python library that worked pretty seamlessly. And we ended up actually configuring them on a by box basis. So every single box had its own stream. And what that meant was, okay, now we can look at things across a box. We can look at multiple different scans that might not seem correlated in our big reporting, but if you look at problems on a per box basis, you can start to diagnose them a little bit easier. So we've added our logging, we've got our fortnight scanning, we've got our fortnight translating. We now have our new architecture. And this architecture looks a lot more complicated, but it's exactly what we've just talked through. We see Fortifeed putting stuff into the build info queue. Fortnight is fanning things out, taking all those various jobs, putting them into SSC, who then pushes them out to CloudFort again, which then fans back in. So we have a fan out, fan in, fan out, fan in. Something seems wrong about that. And that was sort of something that was digging on our minds for a while of why we have twice as many boxes as we might need. There's already a one-to-one correlation between translations and scans. Everything we translate has to be scanned, and everything we scan must have at some point been translated first. So if they're one-to-one and they have to be serial, we can actually make this more efficient. And the way we're doing this is we are going to take CloudFort and fuse part of it into Fortnight. This was actually a super blessing in disguise thing of putting in the work to re-implement the cloud worker, because now we already had the code that could scan something that had just been translated. All it was a matter of doing was, instead of Fortnight contributing this as a translation to SSC, instead contributing that translation to our CloudFort library, and then just uploading that result into SSC. This had the additional benefit of removing our dependence on this undocumented cloud worker API, which, while seeming very stable, is undocumented. You never know when it might all of a sudden change and add brittleness to your configuration. So we're going to actually combine these two into one. And what we're going to end up with is a simpler architecture. Again, we have our Fortifeed feeding into our build queue, but this time our Fortnight is going to fan out and not just translate, but also scan, and then add those scans into SSC. Now you may notice that we've added another queue here, and this is just because of a quirk of SSC. The quirk being that when you upload results, it's a different API from if you would upload translations, and SSC isn't really able to keep track of what results did I get at what time the way it can with translations. What this ultimately means is Fort Squire, which was priorly relying on SSC to know, hey, what's changed, can't really rely on SSC to do that anymore. And so we introduced a new queue. All this queue does is hold onto all of the objects that came out of Fortnight, and Fort Squire can basically just periodically go to the queue, pull everything down, and it knows, okay, everything in this queue is things that have been scanned since I last run, because there's only one of it and it's the only one pulling it down. We've actually played a little bit with the idea of even removing SSC from this entirely and just replacing it with a database, as that's pretty much all it's doing right now. But we haven't gotten around to implementing that. So maybe a little bit of future work. So that's it. That's our architecture to this day. Like, that is currently running in Pleasanton right now. What I'm going to show you next is basically this same architecture, but with all the bells and whistles on it. I've kept this slide intentionally simple so that it's easy to follow, but the full architecture is this. And I know this is much larger, but all it's really adding is our AWS infrastructure, our logs, and some of the niceties that we have. Things like our chat ops with Slack, where both Fort Squire and Fortnight can report important metrics as well as any errors we might see into our Slack, so we can immediately know what's going on. But this is it. This is the this is the architecture. So before we go into the future work, I want to talk a little bit about our deployment pipeline, because in the process of doing this, we actually engineered, I don't know if it's the best or the worst deployment pipeline that I've ever gotten to work on, maybe a little bit of both. But what we've made is something that I actually find super helpful and I think is worth sharing. So as Adrian mentioned, we don't really start out with much other than a zip file and a set of instructions. There are not builds for Fortify the way that some other software might have. And so what we need to basically do is make those builds ourselves. This ends up being accomplished in the form of RPMs. So what we end up doing is taking that Fortify zip and their instructions and encoding it into an RPM that we can actually push up to our Artifactory and utilize later. In addition to that, we also take RPMs for our various different services, so FortiFeed, Fortnite, FortSquire, and our license itself so that we can have easy updating of that. And we turn all of those into RPMs. This all lives in Artifactory and ultimately goes to serve something called IMaaS. So IMaaS is our image as a service, which is a piece of code that Workday maintains and allows you to take any number of artifacts from our Artifactory and turn them into AMIs. So what we can do is we can take all those RPMs that we work to build, and now we have two AMIs, one for our controller, which is going to be our FortiFeed, FortSquire, Fortify binary itself, and SSC, and one for our client, which is going to have Fortnite and the Fortify binary. This is going to massively speed up our uptime because the less that Terraform has to do to spin up a box, the faster that we can bring up a service and we can rapidly expand our actual scanning and translating capacity. The one place we do end up needing to have Terraform is for secrets. Because we don't want to put our secrets in a company-wide Artifactory, we actually have our own AppSec Jenkins that we use to deploy, we use to hold on to these secrets and to deploy the Terraform from. That way, we can use Terraform, drop our secrets onto the mostly already constructed boxes, and just start everything spinning. And using Terraform, we're actually able to create an entire pipeline in one go. This means that if we have a situation where either we'd like to test out a new patch or a new version, or if we'd like to do some configuration tuning, we're able to immediately spin up an instance, mess with it all we want, destroy it, and it won't have done anything to our production instance. So it's been a massive boon for testing and performance optimization. I highly recommend, if you're able to, try to get as much of this pipeline into Terraform. So what next? We currently have each ticket being triaged manually by one of our engineers, which is an unfortunate situation, but it's what we have to do to get this to a point where it can be automatic. We remember, we don't have to be perfect here. Our estimate is 80%, as Adrian mentioned, and that's about saying, okay, if we send 5 issues to a developer, maybe one of them is a false positive. What this actually means is we're going to need to do a lot of small tuning. And this especially becomes important, not just with our false positive rate, but with our performance, because we're aiming for commit rate scanning. Every time a developer commits to a repository, we want to be able to say, were any new issues introduced, and can we get that ticket back to them relatively quickly? So in order to do that, we've employed a few different techniques. This includes things like the filters and the views that Adrian talked about. But one of our biggest tools has actually been the custom rules inside of Fortify. So without getting into a massive discussion of how static analysis works, in general, static analysis is mostly defined by things called sources, pass-throughs, and sinks. Sources are places that user input can come in, things like a scanner in Java or a Spring web request. Sinks are places where bad things can happen. The runtime exec function in Java, maybe a SQL query that isn't parameterized. So what we basically want to determine in static analysis is, can anything get from a source to a sink? If they can, then there's a path for a vulnerability to be introduced. Now, the way we determine those paths is through pass-throughs. Some of them are super simple, like A equals B. If there is evil in B, there is now evil in A. So if A can get to a sink, then B can get to a sink. Some are more complicated, though, and actually require needing to be encoded in this format that we've shown. This rule in particular is a rather complex case of where it seems like there could be a vulnerability, but there actually isn't because of a weird quirk in the XML parsing logic. And it's kind of hideous, but this is the level of verbosity you need for these kinds of rules, because we're really trying to specifically pinpoint things about Workday or things about whatever company you're working at that are specific, that are unique to the code base. And so we're really hoping that as we work with Fortify and each other to expand these rules, we're going to one day be able to get to that 80-20 ratio. So that's all I have for you. Thank you for coming. If you have any questions, unfortunately we can't do Q&A, but if you will look at our handles, they're both here and you're more than free to reach out. I am handled Sigint and my co-presenter Adrian is Adrian Bravo N. So please feel free to reach out. Thank you for listening.